So you're asking, okay, Bill, part one was lots of fun, but isn't this a lecture on curve fitting? Fair enough, let's talk about curve fitting. Before I talk about curve fitting in terms of regression, let's talk about it in the non-optimization case. So I'm going to give you a collection of points in the plane. So there are n points, each with an x-coordinate and a y-coordinate. And what I'm eventually going to ask for is, could you give me a single continuous curve, in this case a polynomial, although it by no means has to be a polynomial, could you give me a single continuous curve that passes through all of my points? And I'm actually, for the sake of the polynomial, I'll be more specific. You gave me n points. I would like a polynomial of specifically degree n minus 1. I guess that allows the possibility to use a lower degree if needed, but it can have degree at most n minus 1. And the polynomial must pass through each of the points I gave you exactly. In other words, if I plug in the x value of a particular point to the polynomial, I should get back the y value of that point. Before I go further, we're going to use a theorem in a minute, but before I want to sort of justify the theorem with a diagram. I'm going to use this sort of as graph paper. Just to justify why I went from n points to a polynomial of degree n minus 1, I want to do an example. So suppose I give you 1 point. There's 1 point. There is a unique polynomial of degree 0. So remember that a polynomial of degree 0 would be a constant function. It would be this function here, the function f of x equals 1. There is a unique polynomial of degree 0, a constant function that passes through any particular 1 point. Okay, if I give you 2 points, suppose I give you these 2 points, there is a unique polynomial of degree 1, which would be, of course, a polynomial of degree 1 is a line that passes through any 2 points in the plane. And if I give you 3 points, suppose I chose these 3 points here, it turns out that there is a unique polynomial of degree 2, a quadratic polynomial, I'm not going to be able to draw it perfectly, but like that passes through all 3 of those points. And so the key difference there, when you have n points in degree n minus 1, it's because degree 0 is a valid degree, and you only need degree 0 if you only have 1 point. There is nothing that stops you, if you have more than 1 point or more than n points, from still having a polynomial of degree n minus 1. So an example would be, here are 2 points. We know that any 2 points can be connected by a polynomial of degree 1, a linear function. It turns out that for these 2 points, though, there is in fact a constant function that connects them. I could use a polynomial of degree 0, but I'm guaranteed when I have n points that there will be a polynomial of degree n minus 1 that passes through all of them. This polynomial, the one that we construct, the unique polynomial with this characteristic for a particular set of points, is called an interpolating polynomial. Now, if you've done interpolation before, for example, in graphics or image processing or something, or in numerical analysis, maybe you're familiar with the idea of an interpolating polynomial, but you're also aware that for interpolation in practice, for example, if you have 1,000 points, you probably wouldn't want to go compute an interpolating polynomial of degree 999. You'd use some other interpolation method. So I'm aware of that, obviously. I'm going to use the term interpolating polynomial because that is what this function is called. This theorem, we're not going to need this much. I just need to justify this point. We're not going to prove the theorem. This is a theorem that's been borrowed from a different course. What this is saying is basically what I just said, but formally, which is if you give me a collection of n points, guaranteed there will be a unique interpolating polynomial of degree n minus 1 that interpolates the entire collection, with one condition, and I think it's a very reasonable condition, which is that the set of x-coordinates of the points that you give me must be distinct. And why is that? So I'll use this as graph paper again and explain why. If I gave you 2 points with the same x-coordinate, I want a polynomial that passes through all of the points, which means if I plug in the x-coordinate of this point, I get the y-coordinate of this point. But wait, it also means if I plug in the x-coordinate of this point, I get the y-coordinate of this point. But they have the same x-coordinate, but not the same y. In other words, the x-coordinate is 4. What is the value of p of 4? Is it 1 or is it 2? It certainly can't be both. And so that's why it's reasonable to assume that I'm asking for too much. If I give you 2 points with the same x-coordinate, how is the polynomial supposed to pass through both of them? So that's obviously sort of ridiculous. That's why I think it's a very reasonable and natural necessary condition. And so, well, the slides are saying it's somewhat intuitive. The slides always use this very detached, erudite language. I think it's reasonable and natural. And then here's another disclaimer. This section is littered with a bunch of these disclaimers. I don't want people who are interested in learning about interpolation to get the wrong idea from this. This is called an interpolating polynomial. If you want to do interpolation in practice, you might use something like linear interpolation, which would be to draw line segments between each pair of points, and then to use the line segment to estimate the value of the function between the points. Or you could use spline interpolation, which does allow you to connect pairs of points by curves and have the curve be influenced by adjacent points, just not by every other point. The problem with interpolating polynomials is that there is this sort of global nature to them, where if I include this point in the set, the behavior of the function over here will change. And that can become a real mess when you have massive sets of points, not to mention that it can result in all sorts of bizarre numerical problems because I end up with incredibly high degree polynomials. If you want to learn more about interpolation, take a course that covers interpolation. So for our purposes, what we care about, the reason I brought it up, is that what we're going to do is analogous to interpolation. Just what happens if we have more points than the polynomial has terms, basically. But also because the derivation we're going to come up with for regression is going to be very similar to this derivation, and I think this derivation is easier to digest for a few reasons. One of them is that we've actually seen a similar derivation to this one earlier in the course when we were talking about linear and quadratic classifiers. So I know that the theorem tells me that if you give me the set of points with the basic assumption that the x-coordinates are distinct, that there will be exactly one interpolating polynomial of degree n minus 1. Then the question is, how do I find it? So what does a polynomial of degree n minus 1 look like? I think it looks like this. This isn't the only way to write it, but this is a pretty convenient way to write it. It basically is just a linear combination of the product of coefficients and powers of x. So c0 times x to the 0, c1 times x to the 1, c2 times x to the 2, and so on. And obviously x is an unknown, x is an argument to the function, so the only things that I need to figure out before I have the whole polynomial are the coefficients themselves, c0, c1, c2, up to cn minus 1. And if you stare at the expression here, you'll notice that yes, there's plenty of nonlinear stuff happening, but as far as those coefficients are concerned, as far as these are concerned, they participate in a linear way. With respect to the coefficients, the polynomial is actually a linear combination of the coefficient times some stuff. So how do we find the coefficients then? Well, I guess what we want, assuming the necessary condition is met, we would like p of x1 to equal y1, p of x2 to equal y2, and so on. Okay, so we know what p of x1 is going to equal. It's going to be c0 plus c1 times x1 plus c2 times x1 squared, keeping in mind that you've given me x1. If I need x1 squared, I can just go compute that. So the only unknowns that are left over, all of the x's are known, the only unknowns are my coefficients. I know the y's, I know the x's, and really then what I have is a system of equations in these unknowns c. And if I stare at that and I sort of tear it into pieces, I try and break it down as far as with the tools I have for systems of equations, I could turn it into this. I could say that system on the previous slide is actually just equal to this matrix times this vector, and I want the result to equal this vector over here. And this matrix is constant. Once you give me the x-coordinates, I can just go compute the numerical value of this matrix. Same story with this vector. You gave me the y-coordinates, I just go compute them. The only unknown that I have left is this. And so if I call this, I don't know, we'll call this A, and we'll call this C, and we'll call this Y. What I have now is this matrix and vector equation, A times C equals Y. All I have to do is solve this for C to get my coefficients. So I could solve it by Gaussian elimination or whatever other method I want, but I could just use linear algebra to compute these coefficients, even though the polynomial that I'm going to come up with, of course, is nonlinear in most cases, if n is greater than or equal to 2, or I guess if n is greater than or equal to 3. So as with our previous application, there's no reason why, just because a problem is nonlinear, that we can't use linear methods to help solve it. And so I hope that this derivation made sense, because we're going to use it later in a context where a lot more stuff is happening. And I should also add another disclaimer. What I really did here, I know I constructed an interpolating polynomial. What I really did was actually construct a linear combination of these linearly independent basis functions, which happened to be powers of x. And as a result, I ended up with a polynomial. There is no reason that you couldn't use exactly the same technique, but with different basis functions. Instead of the basis functions being x to the 0, x to the 1, x to the 2, you could use any other set of linearly independent basis functions. For example, a set of n linearly independent sine waves or cosine waves or exponential functions. And all of those would work, assuming they're linearly independent, and you could create interpolating functions with those as well. And depending on what you're trying to interpolate, sine waves or something else might work better because there are lots of disadvantages to polynomials, especially if you have things like periodic data. That's all really exciting, and I'd love to talk about that for hours, but it's not this course. There is some other course that covers that, but it's not this one. So why are we talking about it in this course then, Bill? Okay, suppose now that I have taken a large number of observations. Now, this doesn't actually only apply to observational data, but observational data is a very good case study for this. Suppose that I have gathered a large set of observations about that is meant to demonstrate a particular relationship. Now also suppose, I'm going to treat this for this lecture as a given. Suppose that you have already told me, I've taken these observations, I believe that the underlying relationship between x and y is broadly quadratic or cubic or something else. It has some characteristic. Maybe it's linear, maybe it's quadratic. You've already decided that there is a particular trend that you expect to see. You'd like to find a smooth quadratic function that models this noisy data set. So first observation, there are more than 3 points here. So clearly I'm not going to find a polynomial of degree 2 unless I'm really lucky and all of the points happen to lie exactly on a quadratic curve. I am not going to be able to find a quadratic polynomial, a polynomial of degree 2 that goes through every single one of this large set of observations. However, if I view the problem as being a quadratic relationship that I have sampled with noise, that is to say, ultimately there is a quadratic relationship, but that my measurement was inaccurate, then what I want to find is, I want to somehow sift through this and find the underlying curve, where if I consider all of the noise that occurred, all of these points are intending to inform me about the same underlying relationship. That's why this is curve fitting. And this is also, of course, the operative step in performing regression. So I have this, and my task is fit a low degree polynomial, suppose degree 2 is what I choose, to this data. Keeping in mind that there will be error because I've got way too much data, and that probably because it's all observational, I wouldn't benefit from a higher order approximation. Because if I know that maybe these points, that these observations are, that between x and y there is supposed to be a broadly quadratic relationship, obviously I don't care about the real interpolating polynomial of all of these points because it would be an enormous mess. And it would have a horrendous number of terms, and it would probably not tell me anything at all. If I could even compute it, because it could lead to all sorts of other weird numerical problems. So I want to fit a low degree polynomial to my data. What should I do? It might be obvious, just looking at this example, that what I need to do is solve some kind of optimization problem. I want to find a polynomial, which for a polynomial of degree 2, what am I looking at? So f of x would equal a times x squared plus bx plus c. I am boiling down information from maybe thousands of data points into 3 coefficients. I want to choose the coefficients wisely so that I end up with a function that best fits this data set. Okay, best. That word best inherently implies optimization. I want a curve that I suppose minimizes to some extent the error between the real data and the curve that I draw. So it maybe is already clear that this is some kind of optimization problem because I can't expect to get a quadratic function that fits every point, and therefore I want to minimize some measurement of error. Of course, this is going to lead us down a rabbit hole. It's not as simple as just taking what we know about interpolating polynomials. We have to also begin to understand, okay, wait, what does it mean to fit a curve to something, and also what is error? And another disclaimer, of course, I'm using degree 2 as an example. I'm deliberately using quadratic as my example because I don't want us to get locked into linear land. Because we're all so used to doing linear regression, I want to make sure we understand that there is nothing special about linear regression besides the fact that a lot of relationships in life turn out to be linear. I'm allowed to use the same curve-fitting logic for any type of polynomial, or in fact, things that aren't polynomials if I want to. I can actually use the same logic. Really, it doesn't come down to the degree of the polynomial, it comes down to how I measure the error. So that's the disclaimer, although we're going to talk about polynomials and then linear regression in this lecture as well. So here's a set of points. It's a smaller set of observations, so we may be able to talk about more things more concretely with this set of points. If we stare at this, and I say, maybe I think that there is a broadly quadratic relationship or maybe a broadly linear relationship between these, it'll be obvious that there is no way I'm going to get all of these points to sit exactly on a particular quadratic curve. So what do I do? Suppose I decide, okay, I believe that there is an underlying quadratic relationship here. And I know, yes, data scientists in the audience, I know that obviously if I only have 6 points, that's a very bold assumption to make unless I have some other knowledge about my problem. Suppose I do, and I want to fit a quadratic polynomial to these 6 points. It is very likely, unless I'm just cosmically lucky, that some of the points, at least I would say 3 of them, if not two or three of them at least, do not lie on any particular curve. I guess I can assume that I could find a function that passes through exactly 3 of them. Not that I'd want to, because there could be cases where allowing there to be a small error for each point reduces the global error a little bit. But it's reasonable to assume that I'm not going to get every point to lie exactly on the curve. There will be some points that are far away from it. So I should first off define what that means. So I'm going to number the points. I'll start the numbering at 0, because it turns out that's the numbering that I use on the next slide. And I've chosen as an example a curve that happens to pass exactly through 3 of the points, x0, x2, and x5. For all of the points, including those ones, I'm going to define the error, we'll call it epsilon I, and I know myself, and I will probably call this E sub I a couple of times in this lecture. Sorry about that, please bear with me. We'll define the error to be, we'll define it as agnostically to any particular measurement as possible. So I'm going to define the error to simply be the difference between the value of the polynomial at a given x coordinate and the y coordinate of that data point. That's it. I won't use an absolute value sign, I won't use a square. We'll bring those in later. For now, we'll just define the error to be the difference, and that's it. So the error could be positive, the error could be negative. So, because we can't expect every error value to be 0, in particular, these 3 points, x0, x2, and x5, they have error values that are 0 because they sit exactly on the curve, but the other 3 points have non-zero error values. We can't expect them all to be 0. We would like to choose our polynomial coefficients to minimize the total error. And alarm bells should immediately go off. Wait a minute, what's the total error? We have to find some way of expressing total error before we can begin making arguments about what it means to minimize the total error. So what does it mean to minimize the total error? Well, it could mean a lot of things. We have to define error before we have to define total error before we can do that. And this takes us back to part 1. In part 1, we had this question of finding a single simple representative for a large set of data. We could use the mean, we could use the median. We saw this interesting and profound connection between means and medians and a particular way of expressing the global error, whether we square something, whether we take absolute values. We want to leave that door open now too. We don't want to jump right in and assume that, for example, squaring stuff is the solution to everything. We saw earlier that there are cases where minimizing squared error can get us into trouble. So although I don't want to bog us down in too much new notation, I feel like this is warranted. We want to be able to measure a global quantity pertaining to a whole bunch of individual values, these individual error terms. And we do not want to just make up arbitrary measurements. So we want to find some way of measuring total error using measurements of local error with some mathematical grounding. And typically, this is grounded in terms of vector norms, in terms of taking the lengths of vectors. So I'm going to define a vector called uppercase E, and you can all make bets on how long it'll be until I regret using E as a variable name. I'm going to define a vector E to have as its components the individual error terms for each of my data points versus my approximation, versus my polynomial. And so that'll be each epsilon I. You could also view it as taking the y value produced by the polynomial on each input x value and subtracting off the true y value of each point. For a perfect approximation, there would be no error. If I ended up with a polynomial where every single data point actually lay on the polynomial, then the vector E would be the 0 vector. And think about that. So it's a vector. And so if it equals a 0 vector, that would mean we're sitting at the origin. If any point does not lie exactly on my curve, then at least one of these error terms would be non-zero. Do we care which one is non-zero? I would argue we don't. We only really care about some measurement of how many non-zero terms or how far away they are from zero. So depending on which terms have an error, we would not be sitting exactly at the origin. This error vector wouldn't be exactly at the origin. It would be somewhere away from the origin. And the question then is, well, wait, so what do we do to measure how bad the error is? And I realized, wait a minute, optimally, if everything is good, in the absolute ideal case, I'm sitting at the origin. If I have errors, my vector has non-zero components and is away from the origin, how do I measure the global significance of that error? Well, I have a vector, so I could just take the length of the vector. And that's why it's good. I think it's a good idea to frame this in terms of vector norms. I could use the vector norm, or norm is a more general term for vector length, to measure how far away I am from the origin, which is the ideal point, the best possible approximation. I could then try and choose an approximation that minimizes that length, that norm. I may not be able to get a norm equal to zero, but I could at least choose one that is minimized globally. And then the question is, how do I compute vector lengths? And it turns out, so you're probably used to the usual Euclidean length calculation. That's one way of computing a vector length, but it's not the only way. And there are lots of other ways to do it, not just the ways I'm going to talk about today, but I am going to focus on one particular family called LP norms. There's some controversy about how to write the word LP. So, and it's not LP. I'm actually, only as I read this, I'm realizing that LP might have another meaning in a course like this. Depending on who you ask, the notation could be like lowercase l, subscript p, lowercase l, superscript p, uppercase L. I'm going to use the notation of Vanderbee's book because I think the section in Vanderbee's book on this is very close to the coverage I'm giving in this lecture. So I'm not going to arbitrarily change notation unless I have to, and I don't have to here. So we'll use the same notation the book uses. I'm going to talk about a family of norm functions called the LP norms, which do include the most commonly used norms and the ones that we're going to care about in this course. The traditional length operator for vectors is actually the L2 norm. Now, maybe we should ask the question, okay, Bill, you found a way of turning this into a vector problem, and we know you love vectors, but why did you do that? Why can't we just make up an expression for global error? The reason is because if we rely on vector norms, and there is some linear algebra happening beneath the surface that we're not going to worry about, but to be a norm, to define something and call it a norm on a vector, on a vector space, it has to meet certain algebraic criteria, which is really helpful. There are certain geometric things we get when something is a norm versus just an arbitrary summation of stuff. For example, triangle inequalities hold. We can assume that if we scale the vector, the norm gets scaled as well. That's one reason why using norms puts us on more sound theoretical footing. Just like a lot of other stuff in this lecture, I would love to talk about that for hours. The problem is it's not my jurisdiction. If you want to learn about that, take a higher level linear algebra course, maybe Math 311, maybe something like CSC 449, which hasn't been offered in like a million years, but not this course, sorry about that, or come talk to me in the office hours. So what is an LP norm? So there are various different LP norms parameterized by values p, which for our purposes will define p has to be greater than 0. It is actually possible to define an L0 norm, but there is some controversy about how to do it. You have to make some algebraic compromises. Because we don't care for this course, we won't worry about that. We'll assume that p has to be greater than 0. If you want to know about what L0 norms have to look like, look it up on Wikipedia. It has a good summary of the controversy. So in general, if I talk about a vector v, the LP norm for a particular choice of p is given by, this is the notation we use. We use the length operator and then we put a p as a subscript, and it's defined to be this equation here. So we take each component of the vector, we raise it to the power p, or we raise its absolute value to the power p, and then we take the sum of all of those and raise it to the power 1 over p. Let's give a specific example. What about the L2 norm of a vector? So the L2 norm would be this. And we square each individual component of the vector, v2 squared. And then we take the result and we raise it to the power of 1/2. And if we try and deconstruct this, okay, first thing we notice, hey, we don't like raising things to the power of 1/2. We know what that means. Power of 1/2 is a square root. Okay. Also, if we're squaring each component, it doesn't matter that we take the absolute value, because if v1 is negative, v1 squared will be the same whether v1 was negative or positive. There's no need to take the absolute value in the case where we're taking it to the power 2. And if we look at what we get, if we simplify it a little bit, we notice, wait a minute, the L2 norm is just our Euclidean distance operator, our Euclidean length operator. We square each component, add them together, take the square root. Okay, so hopefully that helps to tie back in this definition of an LP norm into maybe more familiar territory, this idea of just the usual Euclidean length or distance operator. Now, let's walk through them in order. The L1 norm, actually, before I just have to be careful. P can be fractional. We can talk about the L0.5 norm. We're not going to do that, though, not here. So the L1 norm of a vector would be, well, okay, the formula would give us this. So the L1 norm would be the following thing. Absolute value of v1 to the power 1, absolute value of v2 to the power 1, plus ... absolute value of vn to the power 1, all to the power of 1 over 1. And if we take that apart, okay, no, power of 1 over 1 means nothing, power 1 means nothing, this is ridiculous, and we end up with this. And so the L1 norm of a vector is just the sum of the absolute values of each component. And therefore, if I choose to measure my total approximation error using my L1 norm, an approximation that has minimum total error will be one which minimizes the sum of the absolute values of each individual error term. I should actually be careful of that. Sum of the absolute values of the individual error terms. What about the L2 norm? So the L2 norm is this. So I've actually folded in the square root symbol there. As as I pointed out a couple of minutes ago, we don't need the absolute value operators this time because squaring it does the trick. Notice that the L2 norm is the usual Euclidean length operator. Now, if I want to minimize the L2 norm, which is what I would want to do if I choose to use this as my measurement of error, then it's sufficient to minimize the square root of this sum. All I have to do is minimize the sum, because the square root operator is monotonically increasing. So if I find the minimum sum of squares, I've also found, if I plug that into the square root, I find the minimum square root. As a result, for optimization purposes, we typically just ignore the square root and minimize the sum of squares. You might notice, if you're familiar with the subject, that in fact this is the objective function we would use in least squares regression, which we are going to talk about in this lecture later on. There's also this very interesting case, the L infinity norm. So wait a minute, infinity is not a number, Bill. How are we able to do that? The idea is if we take the limit of this formula, if we look at this formula and just sort of consider what happens as p approaches infinity, it turns out it converges to something. And the idea is as p gets larger and larger and 1 over p gets smaller and smaller, it turns out they do reach an equilibrium. And it's fortunately for us a case in this lecture where I'm actually sort of glad we don't have to worry about that in this course. Proving what the limit equals is none of our business, but it converges to something that is usually called the L infinity norm. And it turns out that the L infinity norm, there is a typo here, there should be absolute value symbols. The L infinity norm evaluates to the maximum of the absolute value of any individual component. So I guess I can maybe give an example to contextualize this. If v equals -3, let's see, 4, -7, and 8, then the L infinity norm of v would be, let's see, well, maximize, I want to take the maximum among the absolute value of -3, the absolute value of 4, the absolute value of -7, and the absolute value of 8. Sorry about the running off the edge there. And of course, that would just equal 7. And so that's the idea. So it turns out as p gets larger and larger and goes to infinity, it converges to this state where the L infinity norm will just give me back the absolute value of the largest single component of the vector. And we're not going to see, we're not going to derive a linear program to compute this, although you are, because it's going to be an assignment question, so have fun with that. So what I want to do is, I want to talk about, with any of these norms really, I want to talk about how do I compute a polynomial of whatever degree I want that minimizes this total approximation error, using whatever measurement of error I decide to choose. In this case, we'll stick with these LP norms. So we'll set our problem up. First, S is, curly brackets. S is a set of points. There are m points. And we'll assume, as we have been doing, that the x-coordinates of each point are distinct. Now, you might be aware that there could be cases where you take observations and two have the same x-coordinate. You could use pre-processing to resolve that. It actually turns out that there are other techniques that can take care of that. With regression techniques, you can often bring in points with the same x-coordinate and everything will be fine. For the sake of our derivation, we won't do that, though. We'll assume x-coordinates are distinct. So suppose that we have a set of points, m of them, with distinct x-coordinates. Now I want to find a polynomial of some degree that you provide me. You want a polynomial of degree n. And it is reasonable, I think, for me to assume that m is larger than n. If you have 10 points and you want a polynomial of degree 10 or of degree 9, I'll just give you an interpolating polynomial. So that would be my solution there. So we will, I guess, make the implicit assumption here that n is going to be smaller than m. We want a low degree polynomial that approximates, that is fitted to this large number of points. So what do I do? Well, if I want to minimize the L1 norm, what I'm really doing is, I can try and sort of map this out from scratch. If we know what the L1 norm actually is, so the L1 norm would be this. I want to minimize the sum of the individual error terms. In other words, if I'm looking at my error vector E, which is equal to epsilon 1, epsilon 2, and so on, the L1 norm of E would be this. Would be absolute value of epsilon 1 plus absolute value of, okay, these epsilons, of course, are just 3's or w's. And as you know from previous videos, I cannot draw 3's and w's on the screen. The L1 norm of my vector E would just be the sum of the absolute values of each of my epsilons. Now, how does that tie into this? Well, you'll notice that this expression here is epsilon I. So what I want to minimize is the sum of the absolute values of epsilon I. So in a sense, this, I'll just maybe write out one extra step. I won't do it up here. This is what I'm minimizing. I've written it all the way out because my goal in this section, in part 2 at least, is to show all three minimization problems in as congruent a term as I possibly can. So I want to make sure that they're written out in a way that looks as similar to each other as possible. In part 3, we're going to go in reverse and make them look different again for the sake of actually deriving optimization problems that we can solve. So what I'm going to do here first is I'm going to try and unpack this bizarre looking objective function. So it's not linear, and the only reason this one isn't linear is because of the absolute value operator. We'll see later we have a way around that, but we haven't seen it yet. So it's a nonlinear function. We can write the optimization problem as a fully unconstrained optimization problem like this. We can also, basically by siphoning out some terms from the objective function and turning them into constraints, we can write it out as a constrained optimization problem. So I have to give a bit of an explanation for why it looks like this. What I really want to do is, so remember that my goal is to minimize the sum, this sum here. So maybe I'll write it out in full. Epsilon 1 plus epsilon 2 all the way up to epsilon n. That's what I want to minimize. But wait, what's epsilon? Well, my options are either to sub in the value of epsilon directly into the objective function, which is actually what I'm doing here. I'm sorry about the inconsistency. Obviously, the position of y versus this sum is different here. You might agree it's fine because I'm taking the absolute value, but I am aware of that inconsistency. So what I could do is I could just sub in the formula for epsilon 1 directly into the objective function, or I could make it a constrained problem as a clever way of backdooring in a definition of each epsilon. I could say, well, epsilon 1 is going to equal this. It'll be this sum here, j equals 0 up to n of cj x, it's going to be pretty ugly, xi to the j, and then that's going to be all minus yi. So this is my clever way of using an equality constraint as a way of defining a variable, basically. So I'm adding a variable to my objective function. Keep in mind that my optimization variables originally are the c's, the coefficients. I'm now creating extra optimization variables, epsilon I, and I'm using equality constraints to define what those variables must equal. So I'm changing nothing about the problem. In a sense, what I'm doing is I'm trading some complexity by taking it out of the objective function and moving it into the constraint system. I'm adding constraints to the problem. I have an ulterior motive. There is a master plan here that will become clear in part 3. Now, why did I bother drawing this? Well, it's because you might notice if you look down here that I've defined it in a little bit of a sort of obtuse way. Instead of writing that epsilon I equals all of this stuff, I have for some reason decided to write all of this on the left equals yi. But maybe you can satisfy yourself that they are equivalent. All I've done to get from this expression to this one is rearrange terms. Okay, so why did I do that then? That's probably a question you have. The reason is because the epsilons and the c's are optimization variables and the y's aren't. So my goal was to write this out in something, not in standard form, but in a form that puts all of the optimization variables on the same side of the equality. So all I've done here is I've traded in some of the complexity from the objective function by turning it into a constrained optimization problem where I unload some of those expressions into the constraint system. All right. Now, the problem is I still don't have a linear program. I've got this program where the constraint system is actually linear. This looks nonlinear, but just like in the earlier case, the x values are constants. You've provided me x values. The optimization variables themselves participate linearly. So the values C0, C1 up to Cn and each epsilon, those are treated linearly here. So I have a linear constraint system, but this is not linear. Each epsilon itself, the absolute value symbol on the epsilon, that is not a linear function. We need to find some way around that if we're going to solve this with linear programming. What about the L2 norm? So I can write the L2 norm as a fully unconstrained minimization problem, which basically involves doing exactly what I had before, but putting a square on it. As we've seen before, there's not much difference between the two expressions besides that square. Or I could do what I did earlier, and I could express it in this constrained form. I could unload each of these terms, which is one of the epsilon i's, and use an equality constraint to turn it into an element of this constraint system and get an objective function that's a little bit easier to work with. So those are my options for the L2 norm. For the L infinity norm, I end up with this rather bizarre looking thing. So it's very weird to consider. This looks like I'm doing 2 rounds of optimization. And I mean, I guess I am, because I see min and max. It looks like I have to solve 2 completely separate optimization problems. But it turns out I don't. It turns out this can be converted into one linear program. But it looks a bit odd. And I could also do the same thing that I did before where I unload this into the constraint system. So I take each of these, which is an epsilon I, and I turn it into an equality constraint. All right. But I still have a very bizarre looking, apparently nonlinear objective function. It's not nonlinear for one of the traditional reasons, that is, there's no square roots, there's no sine function, but it has the absolute value operator, which has strange behavior, and it has an optimization operator, the max function. And we'll see that it turns out that this max function is not really an optimization function because it's doing discrete optimization. It's just picking which of this finite number of things is the largest. So it's not the same as the continuous optimization that we're used to doing with minimization and maximization. Okay, so these are definitions of the problem that we eventually want to solve. What does it mean to fit a curve? What options do we have to define the error? And for these 3 options, L1, L2, and L infinity, what does the optimization problem look like? But we still haven't gotten anywhere. How do we solve these problems? How do we find the polynomial? We'll discover that we can find the coefficients for L1 regression, using the L1 norm. We can find that with a linear program. It turns out we can find the coefficients for L2 regression using linear algebra and no linear program. And it turns out, as you'll learn on the assignment, because you'll derive it yourself, that we can compute the L infinity norm. We can minimize that also using a linear program. So I will defer the discussion, the derivations of all that stuff to part 3.